Hi class. I wanted to continue our discussion of asymptotic expansions with a simple example of how to obtain the asymptotic expansion for a function given by an integral expression. We're going to eventually talk about 4 different methods for this. The first is what we're talking about here, is a very simple method based on integration by parts. A second is Laplace's method, and then we'll start to talk about integrals with imaginary functions. With complex functions, we'll talk about stationary phase and steepest descent. So let's start by talking about an example, the incomplete gamma function. This is the definition of the incomplete gamma function. It's the integral from x to infinity of e to the minus t to the minus p minus 1 dt. And we're interested in examining the behavior of this function as x goes to plus infinity. We expect, after all, the range of the integration is going to go to 0, and the integrand is also steeply falling as a function of t. We expect that the integral is going to go to 0 as x goes to infinity. But we'd like to understand exactly how fast the integral is going to go to 0 as x goes to infinity. Well, one way to do that is to look at this integral, the integral from x to infinity e to the minus t to the p minus 1 dt, and recognize that e to the minus t dt is just d of minus e to the minus t. So then we do integration by parts, and the upper value of the integral vanishes, so all we get is the lower value, e to the minus x over x to the p plus 1, minus p plus 1 times the integral, basically the incomplete gamma function, but with one higher order, t to the minus p minus 2. And we could play this trick over and over again, and we see that the terms that we get are e to the minus x, 1 over x to the p plus 1, minus p plus 1 over 1 over x to the p plus 2, p plus 1 times p plus 2 over x to the p plus 3. That is, we find that the incomplete gamma function is e to the minus x times an inverse power series as x goes to infinity to positive infinity of p plus n factorial over p factorial minus 1 to the n over x to the p plus n plus 1. And we can do exactly the same kind of analysis we did at the end of the last video to show that this is in fact an asymptotic series as x goes to plus infinity. And you'll see that the first term makes sense. The function goes to 0 faster than e to the minus x over x to the p plus 1, but in fact what this shows is that's the leading term, and that the corrections are suppressed by 1 over x. We can generalize this procedure to a set of integrals called Laplace integrals. I of x is the integral for over some range from a to b. It's possible that a or b could be infinity, as it was in the previous example. Some function f of t, e to the x phi of t dt. And if we look at the graph of phi of t, we have in mind here a function phi, where phi is monotonically increasing or potentially monotonically decreasing, but has no 0 derivatives inside the interval we're interested in. In the way we've drawn it as increasing from a to b, we would expect that as x goes to plus infinity, the value of the integral is dominated by the right endpoint. And we can extract the value of the integral, we can extract the value of the asymptotic expression by doing a manipulation very similar to the one we just did. We can rewrite e to the x phi of t dt as d e to the x phi of t over x times phi prime of t. Integration by parts then gives us the first term plus higher order terms. If the real part of phi of a is less than the real part of phi of b, as we've denoted here, the leading behavior is given by e to the x phi of b, and then there's subleading terms that are suppressed by higher and higher powers of x as x goes to infinity. So for an integral dominated by the endpoints with no derivatives, we can just use integration by parts. However, it will break down when the derivative of the function is 0 somewhere in the interval or perhaps at the endpoints, in which case we have to generalize this analysis to something that is known as Laplace's method, which we'll discuss next time.